Thanks to everyone for coming, and I want to start by thanking IPAM and Baumik Institute for putting together this fun and exciting event. I'm proud and honored to be part of it. It's actually not my first time coming here to answer the question that Dima posed. I've been here many, many times, and it's great to have IPAM in close proximity. It's an amazing facility, and there are lots of programs I participated in. And this is not the most recent one, but that's one which ran a couple of years ago on AI and mathematics. And it inspired me, for example, to start a new lab at Caltech, and lots of cool results came out of this program. So in fact, in some sense, the talk I'm giving today is due to this. So AI can do all kinds of cool, exciting things. That's why we're here. That's why we're talking. It can definitely develop some forms of reasoning, do various tasks for us, maybe even develop emotions. I don't know, quite possibly. So the goal for the talk today is, can it develop mathematical reasoning beyond our, or at least average or professional mathematician capabilities? So I'll focus on this talk on mathematics and AI, and there are many bridges going both directions. So going from mathematics to AI, I don't mean just linear algebra and probability theory, which underlies most of network architectures. I mean things like geometric deep learning or topological data analysis, where even advanced topics from graduate level mathematics entered construction of better neural nets in better ways. This talk will be framed in some sense in opposite direction, asking a question, how can AI assist mathematics? But this is an illusion. So even though I'll be phrasing this kind of framing most of my talk from this perspective, actually soon enough, or sooner the better, I ask you to put your engineering developer hat, view this talk from computer science perspective, and start asking what would it take to make this happen? And as a result of this process, we'll see that even trying to do mathematics with AI tools will actually sort of push us to do better and develop new things and discover new things from the AI research point of view. So that's the perspective I want to take. So now, as we talk about mathematics, there are many different levels, and it's natural to organize them in terms of complexity or level of difficulty, which probably aligns with how we learn it from elementary school, middle school, high school. Then we go into various math competitions, undergraduate, college level math, and then we go to various graduate level mathematics programs where there are problems of the type that we expect graduate students to solve really quickly. There are problems that we give to graduate students, and if they finish it, they get a PhD. It's something that's quite bigger. And then we go to research level math that we research level mathematicians struggle with. And again, there are several gradations there. Struggle for a year, struggle for 10 years, or well, maybe ending with level of Millennium Prize problems where the scale could be 100 years. So current tools progressed gradually. It wasn't immediate, but they progressed gradually through the top of this hierarchy. And they're moving pretty well. So my question will be, what will it take? What do we need from AI research point of view? Again, I'm inviting you to put this computer science hat as soon as possible in this talk to get to this most challenging and, to me, most exciting level. So that's the perspective I wanted to. And there are a couple of things. Well, this talk is short, so there are basically a couple of approaches we use to solve math problems. Once we already have an idea of what the statement is and should be, we try to prove it. And this is, of course, ideal venue for collaboration between AI and mathematics, especially through the lens of formal languages such as Ling, Rock, Isabelle, and others, which basically provide us a certificate that if you're trying to prove a certain goal, a statement from a hypothesis, you have to find a sequence of Lean steps. So this is illustration of how it would look like in Lean. It's kind of a combo of computer language, programming language, and natural language. And it's reasonably readable, but the output here would be a sequence of logical steps in either Lean in this case or some other programming language. And if it compiles, if it checks out without sorries and error messages, then it means that, yes, we found a sequence that proves the goal statement from the hypothesis. So that's a natural way to implement, to assist this already existing, and in fact, this formalization has been going on for decades, assist this theorem proving from formal perspective with AI tools. Basically, AI could suggest what steps to take, what should be the path of logical steps from A to B, from hypothesis to the goal. So that's one very wide area where AI can help and is already helping. So in the workflow of a mathematician, there are other tasks that we usually do. So before you have a statement that you know you want to prove, such as Riemann hypothesis, many of us believe that it's true, we just don't know the sequence. In order to formulate such a hypothesis, it's usually useful to find examples or counterexamples, basically do kind of experimental mathematics. And sometimes this finding examples or counterexamples becomes a serious challenge on its own, so it's not just experimental for in a toyish way, it's actually quite an important part of what we do. And here there are also many interesting problems, so I want to illustrate yet another problem. So this comes from combinatorics and is part of Ramsey theory. The question is to find so-called Ramsey numbers. These are minimal sizes of graphs, which if you color with blue and red paint, you're guaranteed to find either red subgraph, complete subgraph, or blue complete subgraph of either color. And the idea here is that if you use too much of one paint, you're pretty much guaranteed to find complete subgraph of that certain size of that paint. So therefore, you want to balance it. And the problem here is asking, so the theorem of Ramsey says that such number exists, and it's a minimal number when this condition is satisfied. But to find this minimal number, what you actually have to do, you have to find maximal size subgraph for which it's not satisfied. So then you'll know that you found the minimum. And for instance, this number here is 18, which means that if I'm asking for subgraphs of blue and red size to be 4, so sitting on a diagonal means that we're asking for same size red and blue subgraphs. So number is 18, which means that for 17, the condition, whatever it is, it's maybe not important if you don't like combinatorics, is actually not satisfied. And it's true. There is a counterexample for which it's not satisfied, but counterexample is 1 out of 10 to the 26. So it's a search problem, but it's a very deep search with very sparse reward from ML perspective. And this problem is pretty cool because so this is counterexample of size 5 that guarantees that the previous number is 6. But if you go in opposite direction, trying to increase complexity, it just explodes. And Paul Erdős, who thought about this problem, sometimes is quoted for saying that if aliens come to Earth and ask us for this next number, which is not known, for size 5, R55, we should gather all power of our planet, maybe these days means also AI power, to try to solve the problem. But if they come and ask for 6, we just should surrender. That's how fast the complexity here grows. So I illustrated for you 2 types of processes that we do in average day or research mathematics. Proving something that we already feel confident about, and also finding examples and counterexamples. And I want to point out that both of these processes, they're actually search processes. So the first one I formulated as search for a path of logical steps from A to B. This is especially meaningful with, again, this formal languages like Lean and others. And search of examples and counterexamples is also a search. So if you start thinking about our research from this perspective, then everything starts to look like a search. At least this is how I felt in the recent years, thinking about it. So therefore, I want to formulate mathematics, or at least for the sake of this talk, we can think about many math problems being proving things, disproving things, or finding examples as problems of search, or equivalently, navigating some set of rules where our goal is to find certain particular goals. So it's very much like playing a game of chess where we have to make particular moves obeying certain rules, and our goal is to achieve certain win state. So this is actually very, very suitable for AI. I bring up board games for good reason, of course. And what I want to emphasize is that from this perspective, if you think about this process of doing research as a search for either a proof or a certain instance, what differentiates easy problems from hard problems is the depth of the search or complexity of the search. For instance, what differentiates lean proofs that I showed for problems that I showed earlier from potential hypothetical proof of Riemann hypothesis is that the latter is probably not going to be a short proof expressed in terms of basic steps. It may be short if we invent some new constructions, but unpacking everything probably will produce a very long one. And the same is true for Ramsey numbers, and in this talk, I'll give you a couple of more examples of the same type. And again, I want to think of it as an opportunity for AI research because I came to this field a few years ago thinking about how to apply AI to math, but eventually it channeled me into thinking about how can I contribute or improve AI from AI research point of view. So that's the aspect I want to emphasize in this talk. And I want to talk about this last part today. I think this third point that I'm making on this slide maybe is good or to touch in a panel discussion or otherwise. Okay, so I already kind of alluded to this, but let's spend a few more minutes that from AI point of view, if you're trying to find something like find your way out of a maze or connect A to B, namely hypothesis to the goal, it's a very natural problem for AI agents, in particular from machine learning point of view, reinforcement learning, which plays these board games that I already mentioned, that helps us with LLM training and now is popular as a very general tool, is an ideal environment, no pun intended, for trying to tackle these problems of finding instances or proofs and so on. And the way it works is that agent interacts with environment, for example, sees where it is in terms of maze, or it could be self-autonomous, self-driving autonomous vehicle. And by observing situation, collecting rewards and punishments, it basically learns to make better moves. So that's actually how I operate in my life. So this is good. It's good philosophy, but how do we implement it? So as I encourage you, let's put our CS hats and try to implement. And we have a dozen of basic off-the-shelf algorithms to start implementing it. In particular, if you talk about reinforcement learning, one of the first in modern era is called DQN. This is ancient times by AI standards these days. This goes to 2013. Notice that this is before AlphaGo and things like that. In fact, at that time, AI systems or RL algorithms were trained on Atari games. That was the benchmark before board games like chess and Go. And this is literally the first figure from this paper. It's actually quite interesting. This was one of the first serious works that made DeepMind famous. And there is now even a movie where they talk about how the story went. It's a pretty cool story. It wasn't a success right away. I mean, it was a lot of struggle as usual. But now this is one of the most basic algorithms that is basically modern version of classical algorithm called Q-learning. So it works well. It is something simple enough that we can implement, but the reason I mention it is just an example that there are many others we can choose from, and this is off the shelf, and there may be 15 or 20 more of those, which have individual names and so on. So the question is, how can we pair such algorithms and architectures, namely hammers, with problems that we want to solve, nails? And that's what I'm trying to illustrate. I promised you several examples throughout this talk, so this will probably be my last example. its previous one was from combinatorics. This is from group theory. In fact, not too far. It could be viewed as a combinatorial group theory problem. It could also be viewed as a word problem or computer science problem, interlacing with things like Knuth-Bendix algorithm and many other interesting problems. And this problem is asking for, it also has contact with low-dimensional topology, knot theory, and other areas, so I like it a lot. And the problem is asking to relate interesting starting points you can think about it as navigating abstract graph to one particular goal state, which is trivial presentation. I'll give you a formulation of the problem mathematically in a couple of slides, but this is meant to illustrate, again, computer science perspective. So a problem is about navigating some abstract graph and connecting A to B. So again, it's a search, and it's a pretty broad and wide search. Group theory is, roughly speaking, generalization of problems about symmetries. And symmetries, you can think of them as playing with a Rubik's Cube. So it's natural to compare many of the problems in group theory to Rubik's Cube. So there are many similarities. So in both cases, this is single-player game. I already emphasized that we can think of math as a game in many instances. So in both cases, it's a single player. There are no two players. There are many starting configurations and one winning state that we want to achieve in both cases. And it's actually true that similar states in both cases can have different complexity. But what's different about these two problems is that in Rubik's Cube, at least in 3 dimensions with sides 3 by 3, we know that we can solve it with at most 20 steps. We don't need more. But here, the actual conjecture, Andrews-Corey's conjecture, is even asking whether it's possible to connect every state to a trivial state. So even that's not known. So that's the essence of the conjecture. So the number of steps may be large, and we'll come back to it in a second. So in the first case, it's easy to generate states of varying difficulty through random scrambling. So that's how we build data sets, again, thinking about practical implementation. So in this case, this is not going to do anything useful for us because really hard states cannot be generated through random scrambling. That's already a problem. In particular, related to this is how the distribution of difficulty. And I already mentioned that Andrews-Corey's problem is a search on abstract graph which is not explicitly presented, whereas you can formulate Rubik's Cube problem as a search of a path on a concrete graph which is explicitly presented. So there are these kind of parallels. Anyway, I have to say a few words about mathematics. So that's how it looks in practice. The conjecture says that every balanced presentation of the trivial group, so if somebody tells us we know that the group is trivial, so this is given as part of the hypothesis, and it's defined using generators x1 through xn and has relators r1 through rn. So relators are basically words. So that's why you may think that maybe LLMs and connections to word problems that I mentioned could be relevant. So these relators are basically words in x's and their inverses. And when the number is equal to the number of generators, such presentation is called balanced. So now the conjecture says that every such presentation, if you already know somehow that the group is trivial, can be reduced to this most obvious presentation of the trivial group, where you introduce a generator and kill it immediately via a sequence of very specific moves. So you can think of it as rotations of planes on Rubik's Cube, for example. So again, we see the same pattern that conjecture is asking us to connect A to B. So this is A, this is B, and then there are very specific moves, namely actions for example, a RL agent, if that's how we want to tackle the problem. And the conjecture is open. It's been open for 60 plus years. There are 2 versions where you're allowed to add the stabilization move, which adds and removes a generator and corresponding relator. In either case, it's unknown what the status is. When I started working on it, people told me that it's believed to be false. But now, after spending some time, actually, I don't know why. It's a typical argument would be of the type that we tried hard and we failed, so it seems to nudge us in that direction. But I don't now take this too seriously. So why this conjecture? Why it's interesting? Again, it's been open for many years. In fact, I mentioned that it's on crossroads with several other areas, such as low-dimensional topology. For instance, Agbulut and Rob Kirby are low-dimensional topologists, and they introduced many interesting potential counterexamples to this conjecture, which now stand on their own. So this is kind of a problem on its own, because all of those, or most of those except for one, are still standing and present kind of a problem on its own right. So that was later generalized by Miller, Shoup, and much bigger family. And this work that I mentioned here is relevant to the stable version with additional stabilization move. So again, the problem seems ideal for our AI agents that make certain moves. Think about self-driving car or something else. Learn and repeat this process until they find optimal policy, right? So that seems perfect. The problem here is that early on, and people already recognize that distribution of the hardness is not really favorable to us to work on this problem. And there are several results which formalize this recently. For example, this one from Martin Britson points out that there are easy to write short presentations. For example, this one has only 4 generators, and these are basically relators that they promised you. It fits on 2 lines. And it can be related to the trivial state. So there is a sequence of moves that you can make, but number of moves is 10 to the 10,000. So that's, the path exists, but there is a lower mathematical bound on the length of the path, okay? So this is a big number. It's not million, it's not billion, it's 1 and 10,000 zeros, right? So this is a crazy number. So my question is, how can we teach AI to find this path, okay? So that's the question. And now this becomes, so in other words, now it forces us to put AI researchers' hats and start thinking about this challenge. So from this point of view, the game of chess that wasn't available in 2013 when I shared that paper from DeepMind seems like a very simple game, because game of chess usually lasts 30, 40 moves. And the longest game of chess, for example, this one is longest in professional history, was only 269 moves. So the difference, so the games are short, first of all. It's only a couple of orders of magnitude in terms of number of steps, very different from what we saw on the previous slide. And also the difference between the hardest game and the average game is not that big. It's maybe order of magnitude. The same goes for games like Go. There, everything will be 1 order of magnitude higher, but that's about it. We definitely don't see something like 10 to the 10,000. So that's the distinction. So in other words, if we try to formulate this as a search, be it Ramsey numbers that I was talking about in the beginning, or this problem, what we encounter is search for needle in a haystack, which is completely hidden, and distribution of landscape that we're trying to explore is so rigged that for majority of initial states, like in this problem, it could be that number of operations or actions you need to make to reach the goal state is polynomial in the length of your original presentation. But somewhere there in the sea of examples, the sprinkle almost indistinguishable examples such that complexity jumps to super exponential 1. And that's what Martin Britson and there are other results of the same type tell us. And these are exactly the hard cases. So for example, I believe that Agbulut-Kirby series that I mentioned before fits in this case, and we need to unlock this super exponential complexity sitting inside of this sea of average examples. So in other words, distinction between average and extreme now becomes very, very important. So what we see, and in view of time, I'll not give more examples, but if you start looking at why certain math problems are hard, you start recognizing that it's actually not uncommon, that many problems, easy versus hard, is exactly this difference between learning average case versus learning kind of extreme or the hardest case. So in particular, in Atari games, which I mentioned before, it's easy for agents to learn what not to do. So this is what our parents tell us, to learn, fail sooner. This is very different from what we've seen just a minute ago. We can go for very deep search and be miles and miles or millions and billions moves in and not know if you're on the right path or wrong path. So that's one major distinction. So we can think of these hard math problems very roughly, and I don't think it's just a comparison or analogy I'm making. It's actually good practice to try a Rubik's Cube in really high number of dimensions with very large sides. That's what hard math is like. So I already talked about distribution. So in many cases, the point is that we're interested in this outliers far in the tail. But another way to think about this problem is that we need to learn somehow from average cases to go to that tail, and that means very extreme or really good out of generalization capabilities. So we need to start with some training data where it becomes more and more scarce as we try to go out, and we need to develop AI so that it can jump further and further, not just 40%, not 30%, but maybe million or billion X. So that's exactly kind of challenge that, that it naturally presents. So I pose the problem now from AI perspective, even though my original motivation was mathematics. So let's see what's out there. And this is exciting, at least it's exciting to me, because now from AI research, we also get to something which is almost cutting edge. I showed that problem from DeepMind, and usually we focus on the top part of the diagram. So these are different Atari games. I don't even know their names. And they're distributed in terms of like how well that particular algorithm I showed performed on them. So that was very cool. And this line, which may be hard to see from the back, is human level performance. So much of it is above, but there are a couple of games which are still below, at least back at the time. And there was one particular game which got exactly 0 score. Okay? So it means that that algorithm completely failed. It didn't manage to succeed even once. And the name of the game is kind of obscure. It's called Montezuma's Revenge. But it became very famous in AI research community because it became kind of a challenge. Okay, what can we do? So it looked like that system didn't succeed. So okay, let's go and make it work. And this is how the game looks. So you have to navigate this maze and collect keys. To me, it doesn't look complex at all, but I don't know what's so special about it. But I didn't play Atari games when I was a kid. And then it became a long search, actually, now from AI research perspective. So people try different algorithms. So here you see that same abbreviation DQN that I showed before with various additional letters added because it was adjectives on top of what Deep Q network stands for. And there were lots of iterations on the scale of almost 10 years, the whole decade, until finally we got above average human performance. And now when at least I work in this domain, this is exactly how I feel. So you have to go through lots and lots of algorithms and architectures if the problem is really challenging to find something that works. Moreover, taking something off the shelf, one of these textbooks by now, DQN is definitely something we teach in a typical ML course, is not going to work. So you have to try not just a dozen off-the-shelf tools, but you have to design custom ones. And even in the process of designing custom algorithms, it's a long journey. You have to try lots and lots on a scale of maybe dozens or hundreds of things before it actually does the job you want. So that's why I invited you earlier to start thinking about solving these problems if you really want to solve them from computer science perspective. And the way we operate now, for example, in this lab, which again was largely inspired by event here at IPAM a couple of years ago, is a pretty much same cycle, research cycle of AI developers. So we propose something, some system, we run, look at W and B curves, analyze them. It's important to learn why it didn't work. Most of the time it doesn't work, so it's not going to work for dozens and dozens. And then after this analysis is done, we try to go back to the drawing board, redesign it, and repeat the process. So the only difference compared to labs in Silicon Valley is that our background is we're trying to work on math environments, but that's not much different. I think that's a great opportunity just because in math, it's very easy to receive robust signal if it's yes or no, correct or not correct. So for example, with lean or satisfiability problems, that's exactly, I would say, advantage of math. And here we can test, can we reach superhuman performance? So that's the goal. All right, so I talked about the problem. I hope I motivated that trying to solve or do interesting math is also interesting from AI research point of view, from even engineering perspective. So I'll say a little bit about this particular problem of Andrews queries before concluding. So that's the one we worked on in my lab for a couple of years. And one thing that's obvious from the start, I don't think it's rocket science, is that in order to reach this super exponential length in terms of number of moves, you have to start aggregating basic moves into super moves. That's actually not surprising. That's used in theorem proving all the time. We want to combine, say, basic lean steps into lemmas, lemmas and bigger theorems, and so on. So that's just theory building. But then challenge becomes, so this is already outside of traditional reinforcement learning cycle that I showed you earlier, where agent interacts with environment, because now you start changing action space. And this is a very delicate thing. So learning that, training that is not something that we can learn in a typical course on machine learning. This is now an art, and indeed is a cutting edge of AI research. So this is exactly what we had to do. You can think of it as a multi-agent model where one is actually playing the game and the other or many others actually instruct what to do, how to make changes, and so on. So this is very popular these days. It's like orchestration of several AI agents. And in math, the beauty is that the ultimate judge is mathematics, whether we solve the problem or not. And so in this particular case, we managed to make progress on this Agbulut-Kirby family that I mentioned, reducing the lower bound roughly by a factor of 2. So the original length for this family, which I didn't show you, but here it is, it was 2n plus 7. Now we reduce it to length n plus 11, which is for large enough n is roughly half reduction, which again, first result in 40 years on this kind of problem. The way it happened is that, of course, we worked in this. So this family is labeled by this integer n, and we started with low values of n. We did n equals 3, 4, 5, and so on. And each one was actually very deep and hard search. So it involved very large numbers, like what you see on the slide. If you do it on very few GPUs, you have to be very clever. So that's where this algorithm design and custom architectures were really useful. And then we were actually lucky. So another component of this research was just luck. It happened that we managed to solve this or make progress for small values of n, and then analyzing what the output was, what the solution was for n equals 2, 3, 4, 5, and so on, we started to see the pattern. And that's how this theorem and other theorems in the paper came about. But this was, of course, sheer luck. It didn't have to be in a nice family, nicely organized. But in any case, this problem aside, I just want to mention that mathematics, of course, is ideal because signal is very robust, so we either solve the problem or not. So that's the ultimate judge. And I think I want to leave a few minutes for questions, so or have a longer break. What I talked about in this talk is challenges presented by math problems which involve deep hard searches, be it a proof, for example, or counterexample. And we can call them needle in a haystack type search, or black swan is also another term which describes pretty much the same, where we look for something which is rare and hard to find, but we really need to find it, like the proof of Riemann hypothesis. Once we find, we celebrate big. So these are kind of problems with very disproportionate reward systems, where you look for something which is unique and hard, but you really want to get it. So in financial markets, this is called black swan type phenomenon. And this is not unique to mathematics, not at all. So rare phenomena with very disproportionate impact, of course, exist in many other domains. For example, extreme weather phenomena and financial markets see crashes, not every single day, but once they happen, we kind of better know about, or it would be good to know about them. So from this point of view, I want to paraphrase a quote of famous mathematician Vladimir Arnold, who said that mathematics is the part of physics where experiments are cheap. So I think he was referring to powerful colliders. We may hear about them in other talks, which take large budgets to build and operate. And mathematics, of course, we used to do it with paper and pencil. So I want you to look at this talk thinking that mathematics could be a part of AI research, where we actually are motivated to do same research and find better AI systems, which unlock some of the challenges I presented in this talk. But we don't need to worry about financial data, privacy, or data about weather and climate. We can actually run same type of experiments, think about same type of AI research challenges just within environments of mathematical problems. So with that, I'll thank you for your attention.